Okay, so hi everyone. Welcome to MIDAS Academy, how I design the bridges. I'm Alice, a structural engineer at AECOM. Today, I'm going to share with you about how I modeled a three-span steel composite Girder bridge design using MIDAS Civil. This was a project that I did back at my first year at work, so I'm very excited to share this with all of you. Hopefully that you will find some useful tips and tricks from this session. So before I start, I just give a quick introduction of myself. I graduated from the University of Auckland back at the end of 2017, studied civil and environmental engineering, specialized in structural engineering. Then I started working at AECOM as a structural engineer. Majority of my work involves bridge and civil infrastructure design, along with helping project and design managers with project management and design management. Over the course of nearly 3 years at AECOM, I have peer-reviewed a number of highway bridges and designed two pedestrian footbridge in Hamilton and Auckland. Some of the notable projects that I got involved include the City Rail Link and Transmission Gully. I'm experienced in both grillage and plate modeling using MIDAS Civil. And in today's webinar, I'll be discussing one of my peer review work, the Pamir Busway Bridge. Hope everyone's looking forward to it. Just a brief introductions about the company I work for. AECOM is one of the largest engineering consultancy in the world. It has over 77,000 employees in more than 400 locations worldwide. It is one of the largest and most diverse provider of technical professionals and construction service. According to the ENR ranking, it ranks as #1 design firm in the world. It has a well-established graduate development program, which I personally participated during my first 2 years at the firm and had a fantastic experience. Recently, in New Zealand has won the City Rail Link project, the largest transportation infrastructure project in New Zealand. I was fortunate to have the opportunity to work on this project as a bridge engineer. So in today's webinar, I'll be first going through some of the project information and getting into the detail of steel composite wizard, time-dependent material, boundary condition, traffic loading, response spectrum, temperature loading, water flow, and wrap up the presentation with the ultimate limit state and serviceability limit state design checks in accordance with the New Zealand Bridge Manual.
Hello, Alice.
Yeah.
Sorry for interrupting.
No worries.
Can you check your microphone setting because some users cannot hear
Okay.
anything? Yes.
Yeah, sure. Is that better?
Okay. So
This,
let's have a time to check some problems.
so I'm using my microphone. Maybe
Mm,
what about now? Is that better?
I can hear you, but other
Uh,
people cannot hear you.
Is this better?
Maybe I'm good, but
Let me know if this works well.
yes,
Is it working?
uh, I have a. Is your are there any button on your portable software like starting broadcasting?
Yeah.
Yes. So
Okay.
yeah. Now we start the webinar. So please
Oh, okay.
Yeah,
Right.
yeah, so yeah,
Okay,
that's
so
why many people are here.
right. Okay. So I'll just go back to the beginning and then start again. Sorry about that, guys.
Please mention
All right. So now we're getting to it. So thanks for everyone for coming to this MIDAS Academy. I'm going to talk about how I designed a 3-span steel composite bridge. I'm Alice, a structural engineer at AECOM, and this was a project that I did back in my first year at work. So I'm very excited to share this with all of you. Hope you find some interesting points and useful tips and tricks from the session. So before we start, I just want to give a quick introduction about myself. I graduated from the University of Auckland back at the end of 2017, studied civil and environmental engineering, specialized in structural engineering. Then I started work at AECOM as a structural engineer. Majority of my work involves bridges and civil infrastructure design, along with helping project and design managers with project management and design management. Over the course of 3 years at AECOM, I have peer-reviewed a number of highway bridges and designed 2 pedestrian footbridges in Hamilton and Auckland. Some of the notable projects that I got involved with includes the City Rail Link and Transmission Gully. I'm experienced in both squarelage and plate modeling using MIDAS Civil finite element software package. And in today's webinar, I will be discussing one of my peer review work in the Pamio Busway Bridge. Hope everyone's looking forward to it. So a bit about my company. AECOM is one of the largest engineering consultancy in the world. It has over 77,000 employees in more than 400 locations worldwide. It is one of the largest and most diverse provider of technical professionals and construction services. According to the ENR ranking, it ranked as #1 design firm in the world. It has a well-established graduate development program, which I personally participated during my first 2 years at the firm and had a fantastic experience. Recently has won City Rail Link, the largest transportation infrastructure project in New Zealand, along with 2 other design firms. And I was fortunate to have the opportunity to work on this project as a bridge engineer. So in today's content, I will be first going through some of the project informations and getting into the detail of steel composite wizard, time-dependent materials, boundary conditions, traffic loading, response spectrum, temperature loading, water flow, and wrap up the presentation with UIS and SLS design check in accordance with the New Zealand Bridge Manual. The bridge we're going to discuss today is located in Pamio, Auckland, New Zealand, across the Tamaki River. It is a part of the Auckland East Busway project. Our client is the Auckland Transport, and the designer for this bridge is from Becker. The design feature of the Pamio Busway Bridge include provision of 3.3 meter wide bus lane and a 4.97 meter wide footpath and cycleway, incorporating viewing platform at each abutment and pier on the northern end of the proposed busway bridge. The scope of the project include eastern and western abutment retaining, approach embankment, battle slopes, and shared path connecting the rotary walkway on the northern side of Pakuranga Road. For this bridge, my role is being the peer reviewer, reviewing the design of the 3-lane steel composite bridge. It is a 3-span steel composite I-girder bridge for a total of 206.5 meter long, and it spans 66.5 meter on the end and 73.5 meter as a main span. It is supported by abutments on either end and 2 large piers with 8 piles each between spans. The superstructure comprised of 2 parallel composite steel I-girder supporting the road carriageway, footpath, and cycleway, with no vertical structure above the deck level. The girder are hunched, varying in depth from approximately 3.8 meter over the river pier to approximately 2.3 meter at midspan, both for economy and shaped for architectural reasons. Steel cross girders are provided between the main girders at 3.5 meter centers. The girders are continuous over the pier bracing between girders is provided at 10.5 meter from the piers to limit the buckling length of compression flange. The deck slab consists of 125 mm thick precast concrete deck panel spanning between the cross girder with a 125 mm thick cast in situ concrete topping. This shows the cross section of the bridge with the pedestrian cyclist on the left and 2 bus lanes on the right. We were commissioned to check the capacity of the superstructure, substructure, connections, and the service brackets of the bridge. On this job, my main role is to build the global model for the bridge superstructure and substructure analysis, which I will cover from the next slide. So before we dig into the steel composite wizard, let's take a look at the overall workflow I used when building the global model together using MIDAS Civil. I first set up the material and section properties. Because the section need to be tapered, I select the composite steel I section under tapered group. It is important to check the properties to make sure everything are correct. Then I use the steel composite wizard to set up the main superstructure on the bridge. It offers some very handy options for setting up the model, and I will be covering more in details later on in the presentation. The third part is to build a full geometry of the bridge. As Steel Composite Wizard only covers a portion of the model setup, I had to use the common tools under Node Element tab to build the rest of the bridge. Once I completed the full geometry of the bridge, I started applying various loading, time-dependent material for construction staging, and conduct eigenvalue analysis for seismic loading. Then I applied the moving load to simulate the forces that the bridge experienced from vehicles. It is worth to run the model a couple of times when building it to make sure that the model behaved as expected. Finally, I create load combinations using the New Zealand bridge manuals to complete the models for design check. The Steel Composite Wizard starts with the basic geometry and with the options of including substructures. For this bridge, the general geometry is set up with the piers to simplify the process of building the rest of the substructure, such as pile caps and piles. One tip for using the wizard is to identify and input all the material and section properties in MIDAS Civil before using the wizard, so it is faster to set up the geometry, loading, and staging. When you set up the wizard, you can save it by clicking the Save As button down at the left bottom end of the display form, as shown over here. The input parameters can be obtained from design drawing, which we used for peer review. The elastic length stiffness defines the boundary condition between the piers and superstructure. A common value we use for stiffness is 1 to the power of 9 or 10 to mimic the full fixity property of the pier bearings. Depending on your bridge structure, there's also an option to turn on the pier caps. Before our modeling, we decided not to. The bridge is designed with 2 main girder beams running across the bridge. It is symmetrical from the middle, so setup for bridge module has been relevantly easy. The wizard provides a pictorial guide for some of the parameters, so it's very straightforward for input. When finished set up the geometry of the bridge, it is good practice to save the wizard and run it. Check that the output geometry is what expected. A quick run through. In this tab, you can allocate material properties of the deck girders and bracing along with the deck thickness. There's only 2 eye girder running through the entire length of the bridge, so you can see on the right side, there's 2 girder with this 3.325 meter offset. A useful tool too, you can see down the left corner is you can copy over the girder geometry from one girder to the second girder. So this way it saves you a lot of time when trying to build 2 girders that are symmetrical. The bracing details allow you to define bracing type and shape. because the cross brace on the bridge is 3.5 meters away from the pier. So I use spacing distance to define the position of the bracing. This part of setup automatically generates the boundary condition and geometry of the bracing, which I use to speed up the process later on when I refine the detail of the bracing. In the brace detail menu, you can select different bracing type and details. For this bridge, there are two types of bracing, the cross beams and bracing at the pier, which you can see on the right-hand side. The guide provides you with the detail on those items mentioned. I used inverted V-brace for the design, and later on adjust the position to suit the design. This function allows you to set up various types of bracing, which saves a lot of time from manually drawing the model. Over here, you can input typical design force, which will save you time afterwards. The wizard allows you to add loads such as self-weight, wood concrete, barrier. Because it's a highway bridge, live loads such as traffic load was also considered. And you can add on the live load over here. I suggest people to play around with this section of the wizard and see what loading output you get in the actual modeling space. This will provide you with some confidence around the actual load application using the wizard. I use the wizard to define traffic lane and vehicles, save time assigning them later on in the process. The display form from both paths are the same as applying moving load in the modeling space, so there's actually no difference. The construction staging for the bridge consists of 10 steps with 2 stages of dig pour sequence. The wizard allowed people to specify negative moments only, which correlate to the middle good span length shown at stage 4. The model captures all construction staging of the bridge to capture all design scenarios through the full construction of the bridge. Because the construction sequence for this bridge is quite complicated, I also use steps in construction staging loading to capture different timing for the concrete pour. The construction staging for this bridge reflects the actual work. If you need to create the construction staging from the model from scratch, then a good practice is to ensure you have the correct structure group, boundary group, and load group when setting up the model. The process for modeling can be very tedious if you don't set up the groups correctly from the beginning. So as what the picture showed, we first activate the substructure of the bridge with piles, pile cap, pier, and abutment. Activate along with the soil springs and elastic links. Then activate the girder in the hogging moment zone. Make sure that the steel girder is still in the non-composite stage. Then activate the abutment girder span when it's launched from either side of the abutment. Ensure it's a non-composite stage as well. Finally, place the main mid-span girder. Make sure that the girders are acting in the composite at the pier. Then after 28 days, activate the composite stage for all the girders to complete the construction staging. One of the key parts for setting up the model construction stage is the composite sections for CS. It is important to make sure that all components type are either composite or tapered composite when setting up your model material and section properties. The H value and long terms are automatically generated, so you can input a calculated arbitrary value and then check updates or H and update all long term once you complete the setup. It is critical that you do this step correctly as it can significantly affect the result you get. The steel composite bridge wizard is a great tool to help the designer build the superstructure of the bridge, as well as applying some basic loading and construction staging for the model. However, it comes with some limitations. For the 3-span steel composite bridge I built, there are some work required after using the wizard to complete the modeling. The first part is building the substructure of the bridge. While the wizard provided a great starting point for building the substructure, the pier cap, building the superstructure, the pier cap, pier, pile cap, and piles need modeling in the actual modeling interface. The deck extension on either side of the bridge also need modeling, as well as the bracing underneath the deck. Those components were built after the wizard. The second part is to apply the tapered section group for the superstructure and substructure of the bridge. Due to the unique geometry of the bridge, I applied tapered section group to the steel girders and pier to finalize the geometry shape of the bridge for the modeling. The third part is to apply the composite information, such as effective width, scale factors, and composite span information. This can be found under the Structure tab, Composite Bridge. The effective width of the bridge is modeled in MIDAS to capture the effect of shear lag. This is compared with manual calculation from the Australian standard 5100.6 to ensure that the model input are equivalent to the Australian standard. Our comparison found that the effective width calculated from the model are very similar to the effective width found from the standard. This was used for the analysis. The time-dependent material is a useful function in MIDAS Civil to capture the creep and shrinkage loading. The creep and shrinkage functions allow you to input parameters from the bridge manual. There are changes in the latest edition of the New Zealand Bridge Manual on the drying basic shrinkage strain, which can be easily adjusted by selecting user-defined options over here. To apply these functions, you need to first define the concrete material, then add in creep and shrinkage and compressive strength button. After that, you need to click on material link to link materials that you want the time-dependent properties. The shrinkage and creep loading is captured after you apply construction stage loading. The boundary condition for this steel composite bridge is quite standard. The bearing design philosophy are as follows. At pier, all the bearings are assumed to carry an equal portion of longitudinal and transverse loading. At each abutment, the guided bearing is assumed to carry all the ultimate limit state, status, or serviceability limit states 3A case in the bridge manual for transverse loading. The guided bearing on either end of the bridge is allowed to fail under large seismic events, which in this case, the concrete shear key will be engaged to provide transverse restraint. In MIDAS Civil, I model the bearing restraint using elastic length. I use a stiffness value of 1 to the power of 10 to mimic the fixity condition in the bearing. The elastic length is a good boundary condition function that allows you to find the resultant load easily through the result table under Result tab. Having the elastic length allows you to output the force that the bearing experiences from the URS and SLS loadings to be able to compare, and for our case is to compare for the peer review with the bearing table that the designer provided. To apply soil spring to the piles, I use a particular workflow to speed up the process. And hopefully some people find this useful for quicker application of soil spring to the piles. So after you construct the geometry of the model in MIDAS Civil, I will go to renumber element ID under the Structure tab to renumber the pile node ID in ascending orders. Then go to Boundary Type and click on Point Spring to apply soil spring. I would input an arbitrary number such as 1 to the stiffness of the spring for all pile springs, so a table is produced. Note, for construction staging, make sure to define the boundary group for all the pile soil spring so you can easily add boundary group to construction staging later on. In the point spring table, I will order the pile in ascending order by the node ID. This way, all the pile soil spring are in the order from the top of the pile to the bottom of the pile. Then I would copy and paste the soil spring value from an Excel spreadsheet that contain all the soil spring value provided by geotechnical engineer to the point spring support table. This makes sure the application of soil spring value much easier, particularly for people with structures that contains a lot of piles. The traffic loading in the New Zealand Bridge Manual consists of normal vehicle load and load vehicle load. The application for loading is quite straightforward, with 120 kilonewton axial load spaced 5 meters apart and a UDL of 10.5 kilonewton per meter for normal vehicle load, and 240 kilonewton axial at 5 meters apart with a UDL of 10.5 kilonewton per meter for the overload vehicle load. There's a reduction factor depending on the number of load lane, and the dynamic load factors depend on the type of structures and the clear span length. So now let's have a look at the application of traffic loading in MIDAS Civil. I choose Canada load for moving load application as the reduction factor between Canada load and New Zealand bridge manuals are the same. Transverse lane optimization are turned on to conservatively analyze the bridge subject to moving load, covering all case scenarios. Application of vehicle loads on pedestrian cycle lane as well as to simulate the worst case scenario. This is applied on all 3 lanes on the bridge and will capture in the result and design chip. The fine moving load case allow you to set up different loading scenarios with different vehicles on different lanes. When checking the result for moving load case, you can use the moving tracer to see which vehicles and load case is causing the critical moment shear demand on the bridge. This will give you a bit more confidence that the moving load case makes sense when predicted scenarios. There are 2 types of seismic loading that is considered for seismic: horizontal and vertical seismic load. The horizontal and vertical seismic load is dependent on spectral shape factor, hazard factor, which is based on the regions you're in, the return period factor, and the near fault factor. The application of horizontal seismic load is dependent on the natural period of the structure, which I use eigenvalue analysis in MIDAS Civil. The slides show the elastic side spectral formula in the New Zealand 1170.5 standard for both horizontal and vertical seismic load, as well as the spectral shape factor. The picture down at the left bottom column is the response spectrum that we use for the bridge. In order to add seismic load in your analysis, the first thing you do is add eigenvalue analysis. Depending on the structures, you can adjust the number of frequency you want the analysis in order to get a higher mass participation ratio. After you find the natural period of the structure through eigenvalue analysis, you can use standards to calculate the response spectrum for the structure, which feeds into the RS functions in MIDAS Civil. I usually have a separate spreadsheet to calculate the profile and feed into MIDAS Civil. After you add the RS functions, you can create load case where you can specify the direction of the seismic excitation, the scale factors where you need some iteration to calculate. So to upsize from equivalent static base shear result and the response spectrum result. The model combination control is where you can choose to add the direction sign to the result, as well as choose between different seismic analysis method. Note, for adding the signs to the result, there's 2 options. You can add along the major mode directions or along the absolute maximum value. If select along the absolute maximum value, it can be the maximum value in different directions, which can cause an abnormal deformation in the model, whereas selecting along the major mode directions will give you a real deformed shape under seismic loading. It's good to note that seismic acts in both directions, so sometimes breaking down the load result checks for dead load, live load, and seismic load, then added together to find the maximum moment demand, rather than purely rely on the load combination you get in the model. It's a good practice. To find the natural period for the structure, it is important to check the mode participation mass to see what percentage of mass is contributed under a particular mode. In this case, the first mode is the longitudinal seismic case, and mode 2 is the transverse seismic case. You can also identify this through looking at the deformed shape of the structures. This can be accessed through clicking on the mode shape button. After you found the right natural frequency, you can use the standard to calculate the response spectrum profile and apply it in MIDAS Civil. And with some iteration of seismic load comparison between the output from response spectrum and equivalent static phase shear, you can find the right scale factor to apply to the longitudinal and transverse seismic case. This completes the seismic analysis part. For this bridge structure, temperature effect has also been taken into consideration. Section 3.4.6 in the New Zealand Bridge Manual outlines the load application for both uniform temperature change and differential temperature change. In MIDAS Civil, I applied the uniform temperature difference at element temperature load. Because this is a steel composite bridge, I applied the uniform temperature of plus or minus 25 degrees Celsius. For differential temperature, the application becomes a bit complicated. In the end, I choose to apply beam section temperature with the section time being a PSC composite. I calculate the temperature gradient using Excel with bridge manual code and the Australian standard 5100.2 for negative temperature gradient. Then I apply the temperature along the full depth of the steel composite girder. Because the bridge is spanning over a river stream, so a unique load case is the water flow loading. This load case is to capture the water flow loads through the piers in both the transverse and longitudinal directions. I used the Australian standard 5100.2 section 16 to determine the design drag force for applying in MIDAS Civil. The forcing is applied in both longitudinal and transverse direction to cover the critical case scenarios. This was translated into line load on the piles and piers. When we did the analysis of the bridge, we found the water load to be insignificant when compared to seismic and wind load, so it did not govern for the bridge design. For the design check, with the help from MIDAS Civil, we used the Australian standard 5100.6, the New Zealand Transport Agency RR bridge manual for the main bridge, and a British standard for splices check. So we basically extract data from MIDAS through the result tables and then use spreadsheet to conduct the design check for the bridge. For using the wizard, moving load analysis, and response spectrum, we're able to complete the design check for the bridge within the allowed time frame, which proves the efficiency of MIDAS Civil and particularly the steel composite wizard for design. A good practice is to understand the MIDAS result table data, so you can extract it from Excel and process it to find the required demand. It is a good practice to use the result table to extract the loading rather than the model itself, because the value you get are more accurate. The result displayed in the model is good for understanding the behavior of the structures and where the critical loads are located, and where the result table gives you accurate demand values. The bearing design can be checked directly from the model. To check this, you first identify the elastic links that represent those bearings. Then go to the result table, click on elastic link to activate the result table for the bearings. The spreadsheet data shows the loads that the elastic link or bearing is transferring from the superstructure down to the substructure via different load case. You can sort the loading directly from the table or export it to the Excel to do data processing in order to find the critical load for the bearing design. And we use that to compare with the loadings that the designer provided to make sure that our model output gives similar output as what the designer proposed. And that concludes this webinar on how I designed the three-span steel composite girder bridge using MIDAS Civil. And now we open for questions. So I received the question that says, is it a beam element or plate element? So steel composite was set up the model as grillage model, so it's a beam element. So let's go into the actual model because there's a question on the frequency of this bridge. You can see that the frequency of the bridge is 0.42 in the longitudinal seismic and 0.57. So the natural period 1.75 for the transverse. I'm trying to see the questions. Okay. So the power cap is plate element. So let's take a look in the actual model. It's in the plate element, and I use elastic link to connect the pier to the power cap and piles. So for the crackdown lengths of the concrete deck, we actually did a separate deck only model to check the deck reinforcement capacity. So, so for checking the response spectrum and equivalent static method, we first look at the resultant force from the seismic load. So I will go to reactions and look at the longitudinal and transverse EQ value from MIDAS, and then input into a spreadsheet to compare it with equivalent static and determine base shear scale factor, and then apply it in the response spectrum load case. So over here. So for this bridge, longitudinal had an increase of 3%, with transverse being 1. So because we peer reviewed this bridge, we didn't check as a Stratton time method, but we confirmed that the designer used the Stratton time method to check the bridge on the power cap. So the deck topping is precast with 125 mil thickness and the cast in situ concrete on top. So this deck was created using actual wizard. So let me just go back to the wizard part. Give me a sec. Yeah. So you can define under the sections. I believe we modeled as a single deck rather than doing 2 staging, but we did model like the wet concrete pour and the actual cast in situ. So that is covering the construction stage analysis. So how do I model the pier and headstock? So as you can see in the section properties, there's a bottom part of the pier, and the top part of the pier has pier columns. In the actual property, we imported from AutoCAD. So we drawn the sections in actual AutoCAD and imported the top and bottom of the pier using tapered. So this way we're able to make sure that the shape of the pier is what's actually being designed. So from memory, the period of the pier removal was about 2 to 4 weeks. So we used linear analysis rather than non-linear analysis because we believe that the bridge is can be moving in both directions, and it was a design check. So it was mainly checking whether the soil spring that the designer applied is as we intended it to behave. CAD model. So let me see if I can find it. Just give me a sec. I don't think it's readily accessible. But it will just be like basically section drawn. So if I just show this part of the pier, you can see that is the shape on top. Okay. So I guess we can show the steel wizard as well to kind of go through some of the inputs. If I can, sorry. My computer won't let me do it. It's not, I couldn't access on my laptop. If there's any other questions, like a good thing to check is you can see all the outputs. It's very complex, so there's a lot of section involved. And what steel composite wizard helps is to reduce the likelihood of misapply the section. And because you can see it's all in composite, so it set up all the cross beams very easily. So if I turn off the deck, you can see all the grillage sitting on the cross beams and the main girders for all the right section properties. And we also applied section scale factors to cover the behavior of the bridge under seismic conditions. And maybe I can go through the construction staging part as well. So in the road construction staging, the composite section properties all set up over here. The shear lag effect was considered as through the effective width. So you can see that we applied the effective width scale factor, which you can find over here in this composite bridge effective width. So we use a different standard for the modeling part, but we also did manual calculations based on the Australian standards to capture the effect of shear lag. So this is all applied in the effective width scale factor. Any other question? Yeah, so settlement load case is applied as 4 scenarios, and we take the worst case scenarios for this case, and the result of the bridge under settlement. I'm just trying to find that low case. Maybe it should be in there, but I don't know. Okay. Let's move to the next question, the wind load application, and I'll see if I can manage to see the wind load application, the settlement part. The wind load is applied as UDR on the top of the deck level for the superstructure, and then at the pier is for as a line load applied across the 2 piers. The settlement is over here. I can't really show the deformation of it, but it's applied in the west abutment, west pier, east pier, and east abutment with the one UIS case that we use to check for the effect of settlement. So we also look at the pedestrian with traffic as well along the pedestrian traffic along the single eye girder to see the effect of it, and apply the straight traffic lane to simulate the scenario where a car might bypass the pedestrian traffic area to simulate the worst case scenario. We also modeled the viewing deck over here as another beam element extension, And for the moving load, I guess it's worth to show that we choose to use cross beams and use cross beam groups for having the moving load transferred or into the cross beams and then down to the bearings and substructures. And as this is more reflects what the reality the bridge is going to experience. So we can have a look at the bearing table. So we use a general elastic link and apply the free flow and guided bearing. So because it was a design review, we didn't like using the actual design bearing stiffness, but we apply like fixity where the bridge shouldn't move, and free flow for the bearings that allows the bridge to expand under temperature, creeping shrinkage. It was in conjunction in ManuCal, but we didn't use the steel composite design because currently the standard doesn't have New Zealand bridge manu. So what we instead is build the model up to a stage where you have the non-composite and composite scenarios inbuilt in the model, and extract the load data from MIDAS and did a manual design calculation based on the Australian standard AS 5100.6. So I will also just open up the construction staging to show what we applied in the construction staging. So when we did the substructure stage, we activate the whole substructure and then activate all the boundary conditions, the pile spring, pile support, pier cap link, abutment link, and then with the self weight of the bridge in the first stage. And then we activate the girders and the bracing along the midspan girders, and apply the boundary condition like the rigid links. Then we activate the abutment spans, and then the abutment bearings, bearing girders, and abutment span girder props. And then activate the main span of the girder. And then as a lot of staging on the wet concrete pour. And then just going through all that, then do the composite actions, which we also apply the superimposed stick load like barrier utilities and barrier surface. And then we deactivate the construction staging mode at the composite stage. And then deactivated the SDL in long term. So temporary support, is it all right if you elaborate a bit more about the temporary support? So construction loading, we can see in the construction stage analysis. So we have two types of load. One is barrier and one's wearing surface. This is all captured in the construction staging, and it can be applied using the steel composite wizard. So we have about 4 minutes before the webinar ends. Any other questions? Yeah, the self-weight function of MIDAS is used for like automatic computation of self-weight. And I guess a good thing to point out is, depending on your structures, you can either use a simple weight or more accurate calculation, and this is under the structure type. And so under structure type, make sure you turn the self-weight into masses, so to get the self-weight output in MIDAS. And from memory, I believe consistent mass is more accurate way of calculating. So if you have a very sophisticated structure and you want to get a more accurate output, then make sure you turn on that instead of lumped mass. So ship impact load was applied. So under static load case 20 and 21, we applied a nodal load. And interesting factors about the bridge is the tsunami load case was also discussed, but the outcome of that is the bridge itself would not be able to handle tsunami load case. And this was a balance between economy and bridge sufficient design. Yeah. So you can see the ship impact load is applied at both directions. Any other question?
Alice,
Okay. Hi,
I have a question.
yeah, go for it.
I can see the braking and traction load in the load cases. Yes. Is that
Yeah.
carried out from the moving load tracer function, or you just include that load manually?
I believe it was from moving tracer. So we did look at how the moving load behaves and apply that. But I think it's also come with a design check. So we review all the design assumptions that designer makes and then verify it on our end.
Okay. I think you can wrap it up now.
Okay. So yeah, so this is how I modeled the 3-span steel composite Girder bridge. Hope everyone found something interesting or learned something that can apply to build your own bridge models. And it's a great pleasure to be here and share this piece of work that I did back in my first year at AECOM. And feel free to email me or ask me any questions, or if you have any feedbacks about presentations or things that we can all do better when it comes to doing finite element modeling, then please let me know. Thanks everyone for your time and appreciated MIDAS for providing me with these opportunities. Thank you.